Good day. You are listening to the official audio dossier regarding the Niagara Structural Integrity Incident. This file is dated January 2026. The subject matter constitutes a post-incident analysis of the subterranean instability currently affecting Horseshoe Falls. Please be advised, while this is a public release, specific technical appendices regarding critical infrastructure vulnerabilities have been redacted for security purposes. Let us begin with the executive summary. In January 2025, the assumption that Niagara Falls is an eternal, immovable object was shattered. The geological stability of one of the world's most iconic natural landmarks was brought into sharp, terrifying question. It began with the detection of anomalous vibratory signatures picked up by routine maintenance sensors, ghostly signals that should not have been there. This triggered a rapid response geophysical investigation, which uncovered something profound: a sprawling, previously undetected network of fractures deep within the bedrock. This briefing details the events of what is now known as the January incident. We will cover the discovery of a 2-kilometer fracture system and the existential threat it poses, not only to the physical existence of the falls, but to the critical hydroelectric infrastructure that powers a significant portion of the North American grid. These findings have triggered a tense standoff between engineering necessity and environmental ethics. We are looking at a potential collapse scenario capable of disrupting 2.5 gigawatts of clean power and threatening riverside communities. Consequently, the region currently exists in a state of high-alert paralysis. This narrative serves as the definitive chronicle of the scientific findings, the technological mobilization, and the complex socio-economic dilemma facing decision-makers in the United States and Canada today. Section 1. The January Incident. To understand the crisis, we must look back to the winter of 2024 and 2025. It had been an uncharacteristically severe season for the Niagara region. The rock face was subjected to punishing freeze-thaw cycles, expanding and contracting the stone. However, the event that triggered the crisis was not atmospheric, it was subterranean. In early January 2025, during a routine sweep of the maintenance tunnels that snake beneath the Canadian side of the river, piezoelectric sensors registered a disturbance. It was a low-frequency harmonic vibration. Now, you must understand that the falls are noisy. There is always a rhythmic rumble of falling water. Engineers have filtered out that background noise for a century. But this vibration was different. It was irregular, it was spasmodic, and it was emanating from deep within the substrate. Thomas Vance, the lead maintenance engineer on duty, captured the mood perfectly in his initial log. He wrote, "It wasn't the water. It felt like the rock itself was grinding its teeth." Within hours, this anomaly spiked. The vibration wasn't staying in one place, it was propagating through the bedrock. Recognizing the potential for a catastrophic shearing event, the Niagara Parks Commission, in conjunction with New York State Parks, activated a Level 3 geotechnical emergency. The mobilization was immediate and technologically overwhelming. Within 2 hours of the alert, a specialized geophysics team arrived on site. The urgency was driven by history. Rockfalls at Niagara are common, but they are usually surface-level events caused by gravity and simple erosion. This signal was different. It suggested a deep-seated structural failure, a rot from the inside out. The team deployed a dual-frequency, ground-penetrating radar system. By utilizing 100 MHz frequencies for deep penetration and 400 MHz for high-resolution surface detail, they began to construct a cross-sectional image of the Earth beneath the roaring water. Simultaneously, seismic arrays were laid out. Geophones were spaced every 5 meters along the accessible banks and tunnels. The team detonated controlled microblasts to generate seismic waves, allowing them to measure the velocity of sound as it traveled through the rock. The results were processed rapidly by on-site supercomputing units, and they were chilling. The data showed that the seismic waves were slowing down significantly in specific zones. In geophysics, this is a telltale sign. It means the sound isn't traveling through solid rock anymore. It is passing through fractured, air-filled, or water-filled voids. By the evening of that same day, the scope of the problem required even more granular data. Dr. Lena Marovich, a renowned specialist in rock mechanics, led a sensor team to install distributed acoustic sensing equipment known as DAS. This involved running advanced fiber optic cables through existing boreholes and drainage galleries. Unlike traditional sensors that measure data at a single point, DAS turns the entire length of the fiber optic cable into a continuous microphone. Dr. Marovich's team streamed live data throughout the night, creating a three-dimensional sound map of the bedrock. What they heard was the sound of the earth cracking. The data revealed strain rates, which is the speed at which the rock is deforming, that were approaching critical failure thresholds. Section 2. The geological reality. To fully grasp the danger, we need to analyze the geology. We call this the stratigraphic trap. Niagara Falls exists due to a specific geological layering like a cake. A hard, resistant caprock of Lockport dolostone sits on top. Beneath it lies a softer, easily erodible layer of Rochester shale. Historically, the falls recede because the water wears away the soft shale at the base, leaving the heavy dolostone hanging unsupported until it snaps off. This is a natural process. However, the January investigation revealed that this process had mutated. The mapping revealed a fracture network that defied all previous geological models. First, consider the extent. The fractures were not limited to the immediate lip of the falls. They extended over 2 kilometers upstream, running beneath the riverbed and, crucially, beneath the hydroelectric intake infrastructure. Second, consider the depth. The cracks plunged to depths exceeding 80 meters. They pierced through the hard dolostone and went deep into the underlying strata, and extending well below the depths of the deepest human-made observation tunnels. Third, the width. While some fissures were hairline cracks, the radar detected branching voids and solution channels as wide as 150 meters in aggregate span. Individual voids were narrow, perhaps 30 centimeters, but they were interconnected, creating a lattice of weakness. The most alarming finding, however, was what we call hydrodynamic sabotage. The solid caprock of dolostone has thinned dangerously. In critical stress zones where the weight of the river is heaviest, that solid rock layer had thinned to less than 1 meter. Analysis suggested that high-pressure water was being forced into these microcracks. With flow rates over the falls exceeding 100,000 cubic feet per minute, the hydraulic head pressure is immense. This water acts as a wedge, now driving the cracks deeper and wider in a process known as hydrofracturing. Effectively, the river was jackhammering its own foundation from the inside out. Section 3. The risk assessment. The discovery moved rapidly from a geological curiosity to a national security concern. A joint task force comprising U.S. and Canadian officials tasked experts like Professor Samuel Ortiz and Dr. Maya Chen to simulate potential outcomes. Dr. Chen's modeling presented a worst-case scenario that has kept officials awake at night. The model predicted the detachment of a massive block of dolostone, up to 70 meters long, 15 meters thick, and weighing tens of thousands of tons. Unlike a standard rockfall, this would be a deep-seated rotational failure. The sequence would be rapid. First, the deep fractures connect, or isolating a massive pillar of rock. Second, the soft shale foundation liquefies under vibration. Third, the dolostone block shears off vertically. And finally, the block crashes into the plunge pool. Such an event would displace a colossal volume of water, creating a localized tsunami or surge wave capable of overwhelming lower observation decks and scouring the riverbanks downstream. But the threat goes beyond the water. We face an energy crisis, specifically a 2.5 gigawatt threat. The most unique and terrifying aspect of the January 2025 incident is its proximity to human infrastructure. The fracture zone lies directly beneath the intake tunnels for the massive hydroelectric plants on both the American and Canadian sides. These plants supply approximately 2.5 gigawatts of clean power. A Professor Ortiz's analysis indicated that a major shifting of the bedrock could shear these concrete-lined intake tunnels. The immediate consequence would be a water hammer effect. This is a shockwave traveling through the pipes caused by a sudden blockage. It could potentially destroy the turbines and flood the power stations. The impact on the grid would be catastrophic. The sudden loss of 2.5 gigawatts would destabilize the electrical grid across the northeast United States and southern Ontario. We are looking at power outages affecting over 2 million homes and businesses, causing cascading failures in industrial sectors during the height of winter. Then, there is the economic and social fallout. Niagara Falls is an economic engine, generating roughly $2 billion annually through tourism. The threat zone identified by the task force encompasses the primary viewing areas, hotels, and boat tour routes. The mere existence of this fracture report has forced a re-evaluation of public safety. New protocols were drafted for a rapid geologic event. These require the immediate evacuation of the river gorge within 10 minutes, a logistical nightmare during peak tourist season. Furthermore, downstream communities, towns and marinas within 10 kilometers of the falls are at risk from the surge of water and debris resulting from a collapse. The collapse of the rock isn't just a spectacle, it is a potential mass casualty event. Section 4. The Remediation Paradox. By late January 2025, the scientific consensus was clear. The falls are unstable. However, the path forward remains clouded by a fierce philosophical and ethical debate. We call this the remediation paradox. On one side, we have the engineering proposal, the surgical approach. Dr. Raji Patel, a leading geotechnical engineer, proposed a bold remediation plan titled the Grout Injection Initiative. The plan is to drill a series of precision boreholes into the fracture zone and inject thousands of cubic meters of high-strength, quick-setting industrial grout. The goal is simple. The grout would fill the voids, displace the water, and glue the fractured bedrock back together, effectively creating a synthetic monolithic foundation. The cost is estimated at $120 million, with a timeline of 6 to 8 months of drilling. Dr. Patel argued his case passionately, stating, "We are not trying to stop nature. We are trying to prevent a catastrophe that we built our infrastructure upon. If we lose the intake tunnels, the economic devastation outweighs the aesthetic cost." On the other side, we have the environmental opposition, the wilderness argument. The proposal met immediate and stiff resistance from the Niagara Parks Commission, environmental advocacy groups, and conservationists. Their argument is rooted in the ethics of wilderness. They cite ecological risk. Injecting industrial chemicals and concrete into a river system is fraught with peril. There is a high risk of chemical seepage into the river, potentially altering the water chemistry and harming aquatic habitats downstream. They cite aesthetic integrity. Opponents argue that Niagara Falls is a dynamic natural entity, not a theme park attraction or a machine to be repaired. By freezing the falls in place with concrete, humanity would be permanently altering its natural state. This debate recalls historical trauma, specifically the 1969 dewatering of the American Falls. Back then, the Army Corps of Engineers considered removing the fallen rock at the base to make the falls prettier. The public backlash then was immense. The backlash now, regarding grout injection, is even fiercer. The conservationist stance is summarized by the slogan adopted by protesters, "Let it fall." They argue that if the rock collapses, it is simply the geological life cycle of the river, and human infrastructure should adapt to nature, not the other way around. As of the release of this report, we are at a stalemate. The situation reflects a modern paralysis. The technical ability to fix a problem is neutralized by the ethical implication of the fix. So the risk of catastrophic failure, which is low probability but high impact, is weighed against the certainty of environmental alteration, which is high probability and long-term impact. Section 5. Technological Vigilance and Future Outlook. While the debate rages in boardrooms, the engineers on the ground have settled into a tense vigil. In lieu of physical intervention, the primary strategy has shifted to hypersurveillance, a digital nervous system. The fiber optic network installed by Dr. Marovich has been expanded. Today, the bedrock beneath Niagara Falls is one of the most monitored geological structures on Earth. The fiber optics detect strain changes as small as a nanometer. Artificial intelligence algorithms analyze the stream of vibration data in real time, looking for precursor signals, specific patterns of microfractures that typically precede a major collapse. The goal is to provide a 20 to 30-minute warning before a major failure. It is not much, but it is enough time to scramble power grid loads and sound the evacuation sirens. Conclusion. In conclusion, the January 2025 incident has fundamentally shifted our understanding of Niagara Falls. It is no longer viewed solely as a majestic tourist destination. We now see it for what it is, a fragile geological pinch point where tectonic forces, hydraulic power, and human dependency collide. The discovery of the fracture network has stripped away the illusion of permanence. The Dolostone caprock is failing. The water is winning. Whether humanity chooses to intervene with millions of gallons of grout or stands back to witness the awesome violence of nature, one fact remains. The geography of Niagara is about to change. The only variables left are when it happens and whether we will be ready when the ground gives way. Technical addendum. For the record, the following technical methodology was utilized during the investigation. The GPR systems used were GSSI SIR 4000 control units with 100 MHz and 400 MHz antennas. Seismic data was captured using geode 24-channel seismographs focusing on P-wave and S-wave refraction analysis. Fiber optic monitoring is conducted via a Schlumberger heterodyne distributed vibration sensing optical interrogator unit. Key personnel recognized in this report include Dr. Lena Marovich, lead geophysicist, Professor Samuel Ortiz, structural mechanics and risk modeling, Dr. Maya Chen, hydrodynamic simulation, and Dr. Raji Patel, lead civil engineer. This concludes the audio dossier on the January 2025 incident. End of file.